Okay, I guess we'll go ahead and get started. Welcome everyone to the climate change session this morning. Our first presenter up is Donald Sampson with the Affiliated Tribes of Northwest Indians. So with that, I will turn the floor over to you, Donald, and you have the floor.
Great. Thank you, Karen. Great to be here. My name is Don Sampson. I'm with the Affiliated Tribes of Northwest Indians, which is 57 Northwest tribal governments throughout the Pacific Northwest. And I'm the Climate Change Project Director. We started the program about 6 years ago. And I want to talk a little bit today about the work we're doing to set national tribal priorities on climate, as well as the infrastructure legislation that is now making its way through Congress. A little bit about ATNI. We've conducted a number of national tribal summits this fall in preparation, and the first one really focused it on tribal priorities for the U.S. Congressional Action Plan on the climate crisis. I'm going to talk a little bit about that today and how that review by a number of tribes throughout the country helped set some national tribal priorities. But of course, we have U.S. Representative Suzanne Bonamici from Oregon, who was a member of the House Climate Select Committee on the climate crisis, and they developed a number of priorities, or the Climate Action Plan, and sought input from tribes across the country last fall in 2020. We also then conducted another summit dealing with climate resiliency across the country, including Representative Deb Haaland, who was there, of course, now as our Secretary of Interior, and she is really now leading our effort to promote climate resiliency with tribes with the Biden administration, as well as others. We then focused in on empowering youth leadership in the climate movement, and then followed up with a session on traditional ecological knowledge. These are all national summits that we conduct with the National Congress of American Indians as one of our partners, as well as other tribes and intertribal organizations across the U.S. This is the session that we had that really was inspiring, but also informative about how we incorporate traditional knowledge into our climate resiliency plans. But this is about the review of the Congressional Action Plan. As I mentioned, ATNI took the lead along with others. Back in January of 19, the House Select Committee on the Climate Crisis created a framework. They had a number of hearings throughout the country, and in June of 20 completed their Congressional Action Plan. Our tribes and others, including NCI, conducted a review of that because we wanted to see what opportunities were there. Here's the members of the committee from throughout both the Democratic and Republican representatives. We worked very closely with Suzanne Bonamici from Oregon. The report and the recommendations set net zero carbon emissions by 2050 and net negative after that. A number of policy recommendations is a 574-page report, and identified a number of investments in climate, energy, environmental policy. These are the 12 pillars. I won't go through the details of it, but 12 pillars of climate action dealing in infrastructure, clean energy economy, new technologies, breaking down barriers for these technologies, investing in workers, pollution and advancing environmental justice, looking at health impacts, agriculture, resiliency, protecting lands, water, ocean, and wildlife, and international leadership, and strengthening our core science institutions. So a big switch from the previous administration and focus on what we're doing today, particularly now in Congress and with the Biden administration. So the purpose of our review was to provide information to tribal leaders, provide them language to use with other policy representatives in Congress, and to create a unified set of tribal policy initiatives. These are the intended audience, as you can see. It was led by a core team. We had 33 co-authors representing different tribes, tribal partners, with additional reviewers, had 106 individuals from 97 different tribes, intertribal organizations through a variety of forums and meetings that we conducted. The review was really to look at information gaps, opportunities, and priorities, but also to identify travel concerns relevant to proposed plans that affect tribes. And then we came out with some overarching travel priorities, which I'll cover next. Some of the key themes was social economic resiliency of tribes during a transition to a carbon neutral economy. Environmental and climate justice, and as you know, this is a big issue in Indian country as frontline communities. And now, of course, we have 5 Native representatives on the Biden administration White House Environmental Justice Council that are really advancing our issues there. Addressing tribal sovereignty and the government-to-government consultation requirements, the ecological resilience and access to our foods, our traditional foods, protection of those foods and the habitats, recognizing our traditional ecological knowledge, and upholding and expanding institutions to engage tribes on climate governance and science. So those are the overarching themes that we came out with. Some of the pillars that we addressed, and specifically for tribes, dealing with infrastructure, environmental standards, roads. Obviously, we're seeing the impacts in infrastructure because of climate, whether it be water infrastructure, flooding, sea level rise. So a lot of these were priorities in infrastructure, as well as telecommunications, looking at the existing oil and gas infrastructure and how it may be affected and affect indigenous communities. The second was to drive innovation and deployment of clean energy. Many tribes are now looking at that opportunity. We have tribes like Navajo that is switching from coal to solar with Kayenta, number 1 and 2, which is large solar project they've developed. Blue Lake Rancheria that are really advancing the use of solar and renewable energy. So these opportunities we think are very important. We want to be able to provide education and make sure that tribes are able to secure funding. And I'll tell you a little bit about some of the funding that's going to be coming down towards the end with the new infrastructure bill. Third was manufacturing of clean energy and our workforce development in tribal communities with tribal colleges and universities and our partners. Manufacturing investment, even clean energy vehicles, zero emission technology. Example, Umatilla tribe, where I come from in Northeast Oregon, we have a large fleet of transit system here, one of the largest in the state, and we want to transition to zero emission vehicles. These types of opportunities we see coming forward with the infrastructure legislation. Breaking down barriers for clean energy technology so that tribes are able to develop these types of projects, and we're working here in the Northwest on both wind and solar as well as geothermal, but the ability of tribes to address those regulatory barriers that oftentimes impede them from advancing clean energy technology. Investing in our workers, we think that's very important. Recognizing tribal sovereignty. We were just talking to members of the Senate Environment Public Works, and oftentimes you'll see where mentioned state and local governments. We want to make sure tribes are recognized, and as much of this legislation deals with advancing economic opportunities for tribes in transitioning from oil and gas development. We were just talking to my friend Nikki Cooley, who's with the Institute for Tribal Environmental Professionals. She's from Navajo, and her family were coal miners and worked in the coal, and now they're transitioning to solar. So I think those are the types of investments we want to make in our tribal communities as well. Addressing environmental justice, recognizing both those tribes that are federally recognized and state recognized so that they are also acknowledged. Making sure that we are advancing indigenous knowledge in each different sector of the Biden administration's federal agencies for environmental justice and addressing the impacts of pollution in our communities. Improving public health, of course, mental health impacts in our communities because of the cultural, social connection to the land, to the fish, the wildlife. We're seeing impacts of mental health with our younger generation as well as elders. Preparing for pre-disaster. and funding for tribal health programs so that we can begin to look at it on a much broader scale than simply from a natural resource base. Investing in agriculture. Many tribes have agriculture down in the Southwest, in the Southeast, as well as in the Pacific Northwest, and seeing how we might be able to invest in carbon sequestration, new strategies for our agricultural production. And then resiliency impacts in our communities, that we can address relocation. We know many tribes, whether it be the Chinamachi in Louisiana, or tribes up in Alaska, or tribes on the West Coast in Washington, that are facing relocation impacts. This is a huge issue. And fortunately, there's some funding that will be coming down, and I'll talk a little bit about that, to support tribes as they lead the effort and not being led by state agencies or federal agencies, and making sure that we have a wraparound approach to addressing this with the federal government, so the tribes can direct how this relocation or resettlement will occur. Of course, the big priority is protecting our land, water, ocean, and wildlife, co-managing. In the Northwest, we have co-management agreements with states, but want to be able to expand that, looking at forest lands, U.S. federal forest lands, co-management opportunity for tribes in the long term, land conservation, heritage sites. So all of these are really critical for our work going forward. And of course, there's been a lot of discussion in the infrastructure bill about how we create and implement infrastructure climate resiliency for natural systems. We think that's a priority that many tribes and environmental organizations are pushing. Climate resiliency and preparedness. Of course, rejoining the Paris Accord, tribes and indigenous people have a very important role in that. We want to strengthen the tribes' involvement in the Paris Climate Accord. We've been talking about how tribes can contribute reductions in greenhouse gas emissions as part of that effort, and acknowledge the work that tribes are doing, along with other indigenous people from around the country and the globe. And then last, of course, strengthening core institutions for climate action, both financial and technical support for tribes and funding. And we'll talk about some of the work that's coming down. The BIA has been the key source of funding for that, and we're hopeful that we can see some additional resources, significant additional resources coming in this next infrastructure bill. So here's what we did. We adopted resolutions. We have a 74-page report, describe priorities in detail. We pushed these priorities with the National Congress of American Indians, United Southern and Eastern Tribes, and we've then advanced them on to NCAI at the National Tribal Leaders Summit that we've conducted. The National Congress of American Indians adopted policy supporting these recommendations. We forward these to the Biden-Harris transition, and now we're talking about national infrastructure legislation. We do have a tribal, intertribal team that is working on the infrastructure legislation as we speak, and many folks might be involved in that, but we invite other tribes that have interest in promoting and advancing some of these priorities with Congress and the infrastructure legislation. It's a partnership with the National Wildlife Federation and Earth Justice, National Congress of American Indians, and others. The action that we proposed at the National Congress of American Indians, as you might know, we have a climate crisis task force that is established with 4 co-chairs from representatives from the Northwest, Alaska, Northeast, Southwest. The chairman of Suquamish Tribe, Leonard Forsman, he's also the president of ATNI, Affiliate Tribes of Northwest Indians, is one of the co-chairs, and they've been working to develop a congressional, executive branch, and international tribal climate crisis action plan. And the framework that we've developed here will be part of that. And of course, we're pressing now for some of the tribal priorities for the infrastructure bill. It looks as though there's a draft of the Senate version that has as much as $218 million, of which about $160 million is for relocation impacts to tribes, and the balance of that will be focused in on tribal climate resiliency planning. As you know, the BIA has been getting about $15 million a year. ATNI, NCI, and others have been pushing to increase the number, that dollar amount and resources to the tribes in a variety of areas. And I'm happy to talk more about that. So that's here's my email. If any of the tribes that are listening or participating want to be engaged in this effort as we move forward with the infrastructure legislation, we've developed a network of about 40 organizations and tribes, and we meet about every 2 weeks. We'll be scheduling another meeting to talk about where the infrastructure legislation is right now and climate resiliency programs that are part of that, so that we can continue to push Congress and the administration to support tribal climate resiliency. So Karen, thank you so much for the time, and I will stop there and hand it over to you.
Thank you so much, Don. We actually did get one question if you want to take a question.
Sure.
This is from Dino. He says, Mr. Sampson, what action steps, programs would you recommend to EPA and DOE to build upon these climate action pillars?
That's a very good question, and I'm really glad EPA and DOE might be participating. You know, particularly with energy, with Department of Energy, a lot of the tribes have been working on, in particular, renewable energy projects, and oftentimes it requires a cost share. There's both the Bureau of Indian Affairs and Department of Energy have a cost share requirement. Example, the Spokane tribe put in about a little over $2 million project for renewable energy, solar, on 9 of their tribal buildings and 23 elder housing. And it required almost $1 million cost share. So that cost share is prohibitive to many tribes. And I think that's something that we need to take a look at. Of course, we need additional resources for tribes to invest in renewable energy. And so we have a series of very specific recommendations that we'd like to forward to them. On the side of EPA, I think EPA has had some programs. GAP, the General Assistance Program, GAP program, has been really the most available program within EPA that I'm aware of. It'd be great to expand their programs specifically for looking at environmental restoration and cleanup, as we're seeing these impacts across the Indian country. So expanding their programs to include more climate resiliency planning and implementation. Out of 574 tribes in the United States, probably only 80 tribes, maybe 85 at the most, have developed some type of climate resiliency assessment and action plan. So we've got a long ways to go to get the rest of these almost 490 tribes engaged in the resources to be able to plan for climate resiliency. So the planning dollars are important, and now we're really gearing up for action. Many tribes, as I mentioned, are facing relocation, direct impacts now, and we've got to address those immediately.
Thank you so much, Don. I don't see any other questions in my chat box. So you may check yours, just make sure you didn't get any in your chat box. And if anyone has any questions after the fact for Don, you're more than welcome to email myself or Karen.
Great, thank you.
And with that, I will pass the presenter privileges over to our next speaker, Dr. Jason Furtado with the University of Oklahoma. Jason, I've given you presenter privileges. You're muted, Jason.
Okay, can you hear me now?
Yes.
Awesome, great. And the screen is showing?
Yes, it is.
All right, awesome. Thanks so much for having me today. So I want to talk a little bit. I know we're in August right now, and it's starting to heat up here in the Southern Plains, but I want to talk about a little bit cooler topic here, and talk about how climate change may be actually impacting winter weather. And this is actually a connection to a lot of climate change that's happening, especially in the Arctic regions here. So as was mentioned, I work in the School of Meteorology at the University of Oklahoma. Of course, this work couldn't be possible without some great students and also collaborators. Oliver Millen is a PhD student in my group. Bailey Jarrett was an undergraduate researcher, and then two colleagues in the state in Massachusetts, Matthew Barlow and Joe Cohen. So as you, let's see if we can advance here. There we go. Well, as we know, our climate system is warming over time due to greenhouse gas increases within our atmosphere. So what I have here is a little movie about surface temperature departures from average, so changes with time, and this is over 5-year chunks, and I'm going to let the movie kind of repeat. It starts in the late 1800s and goes up to 2020. The reds are warmer than the long-term mean, and the blue colors are cooler. And so you can see with time, this map is becoming obviously more yellow and more orange and red. That means the climate system is warming. I want you to pay particular attention, of course, to the north, here in the Northern Hemisphere, most of the warming, a lot of the warming is happening here because we have most of the land across the globe, but especially at the very northern parts. And if you look towards the end of this movie, you can see at the very northern reaches, you can see those really dark reds happening across a lot of Asia, Europe, and into the Arctic Ocean, across northern North America. I'm going to get back to that in a minute, but this is just to set the stage, right? Climate change is happening. And this is on an annual basis. Now, what's happening by season? Well, in particular, I want to talk about the winter season. So what I have here is sort of a snapshot of a trend in December, January, and February average temperatures, the trend starting in 1960 to 2018. And so again, as it shows, much of the Northern Hemisphere here is this kind of red or orange color, meaning it's been warming with time. The scale on the right shows that it's been warming with time. On the left, that little line plot is just taking the average of all those values along each latitude band and sort of showing you what's the average surface temperature change happening per 10 years at each latitude. And you can see that the rate of warming, so that's the trend value, you can see it's higher at the highest latitudes, meaning the Arctic regions are warming faster than the rest of the globe. So while the globe during the winter, or excuse me, the Northern Hemisphere during the winter is getting warmer, the Arctic regions are getting warmer faster. So this is what's happened since 1960. So winters are getting warmer, but something peculiar has actually been happening roughly in the last 30 or so years. So this is the same map, except what I've done is instead I'm calculating the change in temperature, but starting in 1990 to 2018. And you can see that there's some differences here, especially here in the central and middle latitudes here in Central Asia and also parts of North America. You can see now that we're getting some of these white or blue colors, which means actually that temperatures have either not changed much or are actually colder than they were during 1990. So in other words, winters in 2018 were cooler than they were in the early 90s. And again, the graph on the left shows the same thing, but you can see that in particular in the Arctic, that rate is really, really high during this time. So this is kind of weird, right? The climate is changing, it's getting warmer, there's global warming happening, but actually over the last 30 years, our winters across the middle latitude regions have actually been getting either not changing much or actually getting cooler with time. And if I zone in here in the southern plains of the United States specifically, you can see that since 1990, again, this is the average temperature each winter over the southern plains of the United States across from 1990 to 2018, the total trend is actually close to zero. You can see a lot of ups and downs, right? We've had some really warm winters and some really cool winters, but when I average it all out, there's been no change in the winter here. So what's going on? How come we're experiencing global warming, yet our winters, at least over the last 30 years, may actually not have been changing or may actually be getting slightly colder? There's some other evidence of this, that something is going on over the last 30 years. So what I've done here is with my student, Oliver Millen, we've gone back into the observational historical records and looked at cold air outbreaks that have occurred across the central across the Central Plains, and sort of documented each decade how many occurred. And so you can see that, and that's what's on this axis here, is the number of events per decade. And so you can see, obviously, lots of cold air outbreaks during the 1950s, 60s, and 70s. That was actually a cooler period across a lot of the Northern Hemisphere. The number started decreasing until the 1990s, but then you can see that there's been an uptick in the frequency. So again, we're getting more frequent cold air outbreaks occurring over the last 30 years. And of course, if we go back about 6 months, this was what we were experiencing about 6 months ago, one of the most intense cold air outbreaks across the central part of North America. Temperatures across part of the Southern Plains reached almost 40 to 50 degrees Fahrenheit below normal. Widespread snow, widespread ice, truly a historic cold wave that occurred this past winter. And that left us with a lot of scenes like this that are not what you expect to see across Texas, Oklahoma, Louisiana. And of course, there was other impacts from this too, not just the temperature, the science of it, but we had failures in our electrical infrastructure. We had loss of crops and livestock. Unfortunately, close to 170 to 200 people lost their lives due to lack of heating and exposure and long exposure to the cold. Some estimates have several billions of dollars of damages, and this is easily the costliest winter weather event that has occurred in the United States history. So again, this is occurring during a time when global warming is actually accelerating with time. And this isn't just a central United States phenomenon. Other places, Europe and Asia too, as you saw in the map earlier, but a place near and dear to me because I grew up there. I grew up in New England and the northeastern United States. Extreme winter weather is increasing too over recent decades. So what this shows is what I've done is I've gone to 8 cities in the northeastern part of the United States, and I've looked at the top 10 snowstorms in their records, and the records there go back to the late 1800s. And so just take, when did the top 10 snowstorms occur? So these are single day total snowfall that's fallen in those cities. And so you can see all the different colors of the different cities, but what I want you to point it out to is look how much is bunched up towards the end, right? That most of these big snowstorms, these extreme impactful snowstorms, have been happening really over the last 30 years. You might expect that since we've been warming, that the big snowstorm should have happened earlier in the record, not happening in the later part of the record. So we're kind of faced with sort of this paradox. On the one hand, global climate change is happening. Temperatures are warming with time. Winters as a whole, compared to 50, 75, 100 years ago, are warmer than they were. But we're getting these intense, extreme weather, cold air outbreaks that are still occurring, and they're still super impactful. So how can we have this? How can we have winters and this extreme cold air, snowstorms, et cetera, still happening amidst an overall global warming paradigm? So that's what I want to talk to you a little bit about. And what it goes back to, again, is actually looking at an image like this. So what I took was that movie at the very beginning, and I stopped, freeze framed it at the very last image. So this is the temperature change that has occurred just in the last, the 5-year average, 2016 to 2020, what the temperature change was compared to the long-term average. And so again, you can see most of the globe is this yellow, orange, red color. There are a couple of blue areas here by Antarctica, here in the North Atlantic, which is an interesting thing that I'm not going to talk about, but actually has to do with Greenland ice melt. So it's actually a consequence of global warming. But really, it's this deep, dark red at the top. The Arctic is getting warmer faster than the rest of the planet. And this is what we term Arctic amplification. It's a process by which, under global climate change, not everywhere experiences the same trend. And in fact, the Arctic regions experience trends that are higher or more than other regions. So in other words, it's still cold in the Arctic, still colder than it is in, Texas or Florida or anywhere in the tropical belt, but the rate of change is rapidly going up in the Arctic versus the tropics. And this actually has to do with sort of a cycle that happens because of climate change. And so in the Arctic, of course, we have a lot of snow and ice. And that actually acts sort of as a reflecting surface for the Earth's solar, which during the winter isn't much because it's dark up there. But during the summer, it certainly does. It helps to reflect away sunlight, which keeps those areas cooler. But as the temperatures warm, that reflective surface gets lower. We're having more ice and more sea ice and more snow cover being melted. And of course, you may have heard Arctic sea ice is rapidly declining. This is sort of a movie showing that. This is annual Arctic sea ice minimum area. So during the month of September, the sea ice is melting as it is now. September is when it reaches its lowest point, and then it'll start to expand as the polar regions get into darkness and winter takes over. But that sort of contraction of the Arctic sea ice, that minimum area, is getting smaller and smaller and smaller with time. And so what is that doing? Number one, it's reducing that reflection component. Okay, so there's more sunlight that's able to get in. Number two, because there's more exposed ocean, that can get heated by the sun. And also the ocean itself can release heat into the overlying atmosphere. And both of those things cause temperatures to warm even more. So we've set up this cycle or feedback that's happening. We have global climate change. Temperatures are warming overall because of increased greenhouse gases. That's causing more ice and snow to melt at the highest latitudes. That allows for more open ocean, darker surfaces, more absorption of solar, which causes the surface temperatures to increase even more. And the increase even more means there's more snow, more ice being melted. And so you start this sort of spiral, and you can see that in the graph, right? Sea ice is really falling off a cliff, especially since the late 90s and 2000s. Now, to paraphrase sort of a popular saying, what happens in the Arctic doesn't stay in the Arctic. And so what I've been talking about is sort of on the left-hand side of this little flow chart, this Arctic amplification, which leads again to this Arctic sea ice loss, changes in snow cover. Actually, during the fall, we've actually been seeing some increases in snow cover, which again, I'm not going to talk about, but actually has to do with more moisture being available in the atmosphere to produce that. But what this also does is it actually changes the jet stream. And so the jet stream is a river of air in the atmosphere that circles around the planet, and it acts as the storm track. It's where storms tend to form and also track along. That jet stream, actually, the strength of it is actually related to the temperature difference between the lower latitudes of the tropics and the higher latitudes of the Arctic. So when that temperature difference is large, meaning the tropics are very warm and the Arctic is very cold, the jet stream is really strong. When that temperature difference weakens or slackens, think about that sort of like a rope, okay? Now you've added slack onto the rope, right? Well, what happens? The jet stream is going to start changing. And it's going to actually, instead of being tight and wound up close to the Arctic, it can start to slacken and start to get more meanders up and down and up and down. And that's actually really linked to what's happening, because that jet stream, like I said, is a storm track controlling the storms, but it also controls sort of our temperature patterns. And so when we start getting more waviness in that jet stream, that's when we can start having these intrusions of cold air from the Arctic dip further south than we might expect them to occur. And so Arctic amplification is actually doing that, right? It's changing the temperature difference between the tropics and the high latitudes, because although the cold globe is warming, the north is warming faster than the south. So that rate is causing the difference to become less with time. The other thing I want to also talk about that's very important here is polar vortex. And this has been in the news media. You can't get away from it now. Every winter, it seems, there's always a polar vortex. You know, if it's not the attack of the polar vortex, it's a Godzilla El Nino or something that's coming after us. But I want to just sort of describe what the polar vortex is, because it's actually not a new phenomenon in our climate system. It's something that's there regardless of climate change. And so the polar vortex you can think of as a large circulation of air that sits roughly somewhere between 30 to 50 kilometers above the surface. And this is in the stratosphere, which is the layer above where we live, the troposphere, that's where all our weather happens. And it's this big circling vortex up there. And actually, what I like about this image actually from NOAAclimate.gov is that it depicts the polar vortex as sort of a 3D structure, because that's what it is, and it's a bowl actually. So you can think about this big spinning vortex that's sort of this bowl up there. And when that is stable, or when that polar vortex forms, okay, during the winter months, this is when it forms from the cold air. Cold air is very dense, and it allows this circulation, the westerlies, to really wrap up and get stronger. That actually has a control not just way up at 30 to 50 kilometers, but actually that circulation, as the picture sort of depicts, goes down into where we are, and it controls our jet stream. And that's what this blue line is with the arrows, okay? And so when we have a vortex that's stable, think about sort of it's spinning around very strongly. Think about an ice skater. When they bring their arms in, they can spin very strongly. Everything's self-contained within there. The jet stream is further to the north. The storms are further to the north. That also locks up the cold air way up into the Arctic. Now, there are times when that polar vortex gets disrupted, and it's actually, as I'm going to show you in a minute, one of the things that our team is indicating is that this polar vortex is getting disrupted more and more over the last 34 to 40 years. When that vortex gets disrupted, that's sort of, if I go back to the ice skater analogy, that's like the ice skater taking their arms out, right? When they do that, they're not as, they don't spin as fast, right? They're spinning, the circulation goes down, and that allows things to spread out, their arms spread out. Well, that's what happens with the jet stream too. When that polar vortex gets disturbed, the jet stream now is not as tightly wound, and it's able to get more of this wavy nature to it. And remember that jet stream is the boundary between cold and warm air. So if I start introducing waves into it, that's going to let the cold air to start intruding further south. So these disrupted polar vortex events are actually super important for explaining why we've been seeing the extreme weather that we've been seeing over the last 30 years across a lot of the Northern Hemisphere. And just to link it back again to the February 2021 event, we actually had one of these vortex breakdowns occur during January. So the image on the right, that this sort of milky white circulation, it's going to repeat again, that you can think about that as the polar vortex, okay? And you can see it's pretty concentric and over the pole during December. With time, it migrated off the pole, and then you can see it sort of get sheared apart there towards the end of the image. That was sort of our first clue that things were going to get a little bit sort of crazy weather-wise across a lot of the Northern Hemisphere. And certainly that did come to fruition. Of course, that cold wave that I talked about, but other places too had some really extreme weather during late January and into February as well. And it's all linked back to this vortex disruption that occurred. Okay, so I talked about this polar vortex, the jet stream, Arctic amplification. How do I put all this stuff together, right? How does sea ice at the surface, at the very bottom, affect a vortex that's 50 kilometers above the surface that then affects what's going on at this down below? So I have this nice image here from the National Science Foundation. And so the first thing to look at is, in the first step of the process is, when I start heating up the bottom part, so i.e. Arctic amplification, when the surface starts to get warmer, that lets more heat start fluxing into the stratosphere, so into where the polar vortex is. So in other words, I have a reservoir now of warmer air that I can start fluxing or moving into the polar vortex. And remember, that polar vortex, it spins fast because it likes to keep the cold air in. Once I start intruding some warm air, it's going to start weakening that circulation. And that added heat, again, the vortex will start to weaken, and that'll start to slacken or weaken its circulation, and the jet stream will start to slacken further to the south, developing these bigger waves, okay? So the vortex at the top weakens, and then everything below it starts to relax, and we start to get more waviness into the Northern Hemisphere, and that's what brings the extreme weather. So again, lower level heating near the surface can actually be transported in a sort of in a three-dimensional way, so horizontally but vertically as well, to really cause changes in the polar vortex. Okay, so that mechanism that I just showed you, right? This picture that I showed you from the National Science Foundation, is this what's happening right now? Is that what's happening over the last 30 years that's giving me these colder or neutral trends in the winter? And the answer is yes. So what I have here is an image here of the trend, so the change with time of heat flux going into the stratosphere. So this is that heating. This is sort of that first part of that picture that I showed you. The red areas are regions where there's more heat, or the trend is positive, meaning there's more heat over time being added to the stratosphere. The blue is where there's less heat. And you can see in particular that across a lot of northern Eurasia and parts of the North Pacific, and also northern North America, we have had significant, the little stippling black dots mean that they're significant. We've had significant increases in heat going into the polar stratosphere. And so this is sort of checkbox for step one of that process that I just mentioned. And in particular, we're really interested in this region in Northeast Siberia because just in straight climatology, that region is actually a hot spot for heating of the polar stratosphere. So in other words, without any climate change, just because of the nature of Earth's circulation patterns, that region is already a place that we introduce heating, and we're sort of turning the knob up more. So meaning a favorable spot is getting even more favorable. So that's sort of a super clue that the polar vortex should be weakening. And in fact, when we look at the polar vortex strength, and so that's what's shown here, think of these are heights. So think about this sort of as how deep that bowl is that I talked about, as the polar vortex as a bowl. So the positive or red colors sort of means sort of that bowl is getting shallower, it's getting spread out more, it's getting weaker. We want a nice, big, deep bowl to sort of spin around. So the red colors means that the polar vortex is weakening with time, and the blue colors would mean that the heights there are getting lower with time. And so you can see that over the pole, there's a lot of those red and oranges, meaning the vortex is not as deep over there anymore. There's some blue happening here across Mongolia and parts of southern Russia. There's some indication that the polar vortex may actually be shifting a little bit in its mean position towards Asia versus the pole, which is something that we've also started looking into as well. There's other ways we can look at what's happening to the polar vortex. The top left one is every year, what is the average, where's the average center in terms of a latitude? What's the average center of the vortex located? And you can see since 1980 that there's been a decline or a decrease or a southward shift in that centroid latitude, whereas before the centroid latitude might have been somewhere around 78 or 79 degrees north during the winter months. Now it's been shifted downward to somewhere maybe between 75 to 76 degrees. And that sounds small, but again, remember, this is indicating the vortex is getting wobblier, meaning that the jet streams also get wavier. The bottom left is a trend in the size. So this is the total area of the vortex. Again, this is an average per season. And you can see that on average, the vortex is getting smaller. There's a declining trend in that. And that declining trend means, another way of thinking about that is, that bowl is getting smaller, it's getting weaker, the vortex is getting weaker, which again, these are all checking the boxes that we should be getting more extreme winter weather happening. And indeed, now what we're doing is we're looking at trends that are happening, but now in the middle troposphere. So now we're about 5 to 6 kilometers above the surface. This is again where the weather's happening. What's happening to the height surfaces there? So in other words, this is also a proxy for the jet stream. And the red colors means that the heights are getting higher, which also means there's more high pressure areas starting to form in that regions. And you can see that that's happening across all of the Arctic regions, and especially across Alaska and into Eastern Pacific. But you can see 3 very distinct areas of blue, which means this is what in meteorology we would call troughs, which are also areas which tend to have more storminess with them. And you can see that that's happening across a lot of Central Asia, across a lot of Europe, and then right here across a lot of Central North America as well. And so these are, again, remember I said winters are getting more extreme, or winter weather is getting more extreme over the last 30 years. These troughs are telling us that that should be happening, and the trends are verifying that. And in fact, if we were to take a look at this same trend and then ask the question and say, if I was interested in cold air outbreaks across the United States, especially the central part of North America and the central North America, let's say, because it includes a lot of the areas, not just here in Oklahoma and Texas. But if I was interested in cold air outbreaks there, what's the favorable circulation pattern that I would want to happen? And you can see that the favorable circulation pattern is to have a big trough. That's what the blue area means, big trough across this north central areas here, and then big ridge across Alaska and into the Arctic. And you can see that that's exactly what the trend is saying. So in other words, the trend in our circulation pattern is matching the favorable pattern that should produce a cold air outbreak. So when we have a trend matching that, we should expect that cold air outbreaks should be increasing with frequency, and they are, as I showed you earlier, towards the beginning of the talk. And if we flip again to February 2021, this is the circulation pattern in the middle troposphere that was occurring during that event, and you can see there's our favorable big trough right across the Canada-US border, sort of centered there. And again, if we flip back, that's sort of in the favorable spot. So all these things lined up, right? Okay, so sort of to start wrapping up here, let's sort of go through what we've talked about. First of all, global climate change is happening, and especially Arctic amplification, meaning the Arctic is getting much warmer faster than the rest of the other places in the globe. The polar vortex, that way up in the stratosphere, that has weakened with time and shifted more off the pole with time. And that, of course, that more disturbed vortex, meaning it's moving off more over the last 30 years, is sort of yielding more large meanders in the jet stream, and that was creating more of these extreme winter weather events like the February 2021 event, but certainly there are many, many others over the last 30 years. The ice storms that have happened across a lot of heat across North America, Europe in 2018, the super cold that happened there. And that's all inducing this extreme winter weather. So then the next logical conclusion you might say is, okay, well, Jason's pointed this all out, so that must mean that climate change is causing the most recent extreme winters to have happened. And I'm going to put up a little caution emblem there, okay? Because I'm not going to say that that's not true, and I'm not going to say that it is true. What I've shown you are a lot of observational data to suggest that, and a lot of statistics to show that. And so, you know, in climate, of course, we have all this data that we can show you, but in order to prove a mechanism, we like to show, well, in science, any science really, but we like to show reproducibility, meaning this has happened at other times as well, number one. And number two, we'd also like to take sort of climate simulations and take a simulation and do it and show that if I start warming the Arctic, that I should be getting extreme weather. You know, I can't just say correlation equals causation, but certainly the theory here supports, or the data supports the theory. So I'm just going to go to two quick things before I turn it over. One of the things we can do again is this reproducibility, or another way to do that is let's look in history and see, has there ever been other times where the vortex has been weak? So this idea that Arctic amplification is weakening the vortex may be true, but are there other periods where the vortex was also very weak? So what I've done is I've taken one of those measures of the vortex strength that I showed you earlier, and I've plotted it now back to 1900, so the early 20th century. The large values on this mean that the polar vortex was weaker during that year. Those, if you see any dips, or the down values here, mean that the polar vortex was stronger. And so you can see that certainly over the last 30 years, right, there's been a trend up, meaning it's getting weaker. But I would argue that there's been other periods as well, and especially here during the mid-1940s until the 1970s was also another period where the vortex was also weak. So in other words, we can get weak vortex patterns without having to have Arctic amplification. So Arctic amplification is not a prerequisite to have the weakened vortex. The other thing, again, like I said, is climate simulations. So if I take a climate model and I run it out over the late 20th century, do I get these more extreme winter weather? This more extreme winter weather to happen, do I get the polar vortex? So to answer that, do I get the polar vortex weakening with time? Because remember, that's sort of one of the key check marks to link to this extreme winter weather. And the answer is there's very little consensus behind it. And so this review paper that came out in late 2019, actually by one of the people on this work, Judah Cohen, showed that while some model experiments do support the evidence that I've shown you, most of the modeling results actually, when you look at them, they don't have a robust or consistent message with them. So there's a lot of divergent conclusions here. And so it leaves us with sort of, is the Arctic really causing this? And so, we can go on and look at more, but that's sort of where the state of the science is right now. So let me leave you with just some final thoughts here. Recent winter weather trends in observed extreme weather are consistent with the Arctic amplification theory, but we cannot say that they are caused by global climate change. There's also another paper that came out last year that actually we could be actually seeing a trend toward the vortex sort of changing its trend, so that the weakening trend may actually not be occurring as much over the last couple of years. And so the period of this extreme winter weather may be actually reversing or ending. And so, of course, we won't know that until it happens, unfortunately, but there's some evidence that that's occurred, that's happening. And so, but I want to leave this point because I think it's very important. Winters are getting warmer under global climate change, and they will continue to get warmer. But we cannot exclude that there's going to be these extremes like February 2021 that can still occur during a warming winter. So I'll leave my contact information there for you. Of course, email. I have a website where there's lots of publications and members of my team and all that good stuff. And also, if you are on Twitter, you can follow me on that, where I tweet a lot of these kind of things. So thank you very much for having me, and I'll turn it over if there's any questions.
Thank you, Jason. I don't see any of the chat box on my end just yet. So you might check yours. And if you're calling in, you can send your questions to me and I will forward them to Jason. Jason, did you see any questions in your chat box?
I'm trying to, let me see chat. Oh, yes, I do have a question here. It says, with climate change being more recognized than, let's say, 100 years ago, what does the next 100 years look like? Should we expect these trends to continue? How long will it take to reverse Arctic amplification? And realistically, what would be expected from us globally to achieve this goal? Okay, there's a lot in there, but let me try to address a couple of these. So with time, let me address the first part about what sort of the next 100 years look like. I think a lot, once we get beyond the next couple of decades, all of our climate simulations and the projections that are going to happen with greenhouse gases all show that we will be rapidly warming with time, and anywhere between, say, 2 to maybe as high as 5 degrees Celsius above what we had in the late 19th century. So the trends that we're seeing in the winter weather now may be sort of just temporary, and what we're seeing sort of in what I like to call sort of this transition period, where we're sort of in between and sort of ramping up our climate change. Arctic amplification is going to continue. And, again, there's, depending on where you look, when is Arctic sea ice going to completely disappear during the fall months? There's some debate about that. Could be as early as the 2030s. Other people say the 2050s. But Arctic amplification should continue to increase so long as there's enough snow and ice to continue that feedback loop. And then sort of the last part about realistically what can be expected from us, all I can say is we need net zero and even negative emissions right now. And that's a huge challenge. That's a whole other topic about how do we engage that? How do we get policies to get that going? Certainly some of the stuff that was talked about in the previous talk are certainly stepping stones there, at least here. But really it's a global effort that really needs to be done. I have one more question. Is it possible for the jet stream to widen and dip and create surface winds of Neptune proportions? So I'm not terribly familiar with Neptune, but the jet stream, at least the speed of the jet stream, gets controlled by several things, and actually is controlled also by how fast our planet spins, and there's a whole bunch of other constraints to that. So I think the mean position of the jet stream, again, is wavy now. It'll probably continue to meander for a while. But as we start to homogenize things, the jet stream should probably start to lift back to the north, probably in the average, start lifting back north as we start doing that. But again, the wind speeds are really a control. There's a lot of other factors besides the temperature on that. So again, I'm not familiar with Neptune in terms of speeds, but there is a constraint. We can't, it's not sort of an unlimited bound, sort of in the natural part or the top limit part.
Okay, thank you. Thank you, Jason, very much. I don't see any other questions just yet. But we still have time in case you have a question a little later, and I'll watch my email to make sure we don't receive any from the people that are calling in. So with that, we will move on to our next presenter. And next we have Dr. Renee McPherson with the University of Oklahoma. Renee, I have given you, yep, you saw that. So Renee, I will turn the floor over to you.
Well, thank you so much, Karen. And I'm honored to be on the same stage, so to speak, with Dawn and Jason. I'm going to talk a little bit today about our future projections for what we might see in the South Central part of the United States. Before I go into that, I want to recognize our funding from the U.S. Geological Survey, the University of Oklahoma, and the National Science Foundation, as well as our scientific partners at NOAA's Geophysical Fluid Dynamics Lab, who actually developed these projections and work with us on analysis. And then many thanks to those who created the maps, the graphics that you'll be seeing, including one of our fantastic native scholars here, Peyton Kavnar. So let's first get on the same page about this climate modeling that Jason was talking about toward the end. So models in themselves are to essentially help us better understand a system or a concept. And you can look at the gibberish here on the screen, and these are just mathematical equations that we as climatologists recognize very readily. These equations and others explain how temperature, precipitation, or other variables change over time so that we can help predict the future behavior of the climate system. And a global climate model is essentially a numerical model. So these are models that take these mathematical equations and they translate them into computer code. So these computers run that. So all of these equations that describe physics and fluid motion and chemistry of our Earth system go into what we call this global climate model, or GCM. And in the GCM, the Earth is divided into millions of these grid cells, we call them. And so it's kind of like this ginormous spherical Rubik's Cube. The computer itself solves thousands and thousands of equations to get our temperature and precipitation and all of that at each of the grid cells. And so we have to use the world's largest supercomputers to do these trillions of calculations. They operate on these supercomputers for months to get a full simulation out until the end of the century at every time step and every grid point there. Today's generation of GCMs can simulate the things that we would expect to see in our climate system. They can simulate tropical storms and the jet streams that Jason was talking about, trade winds and other features, all from just inputting these equations into the model and then also forcing it by some large scale features like where are the continents and the mountain ranges, how much energy is coming in from the sun, and and importantly for us, what the concentration of different greenhouse gases are, like carbon dioxide. And so these GCMs describe the climate of the region, but importantly, they don't predict the weather at a specific place. So they're not going to tell me what to wear on a given day, but they can generally suggest to me what my wardrobe should be for a certain location and a certain decade. No model can perfectly reproduce our really complex climate system. Mother Earth is much smarter than we are, and so we can't do all of that. But when we run these global climate models in the past, we have produced meaningful results that have adequately represented what has happened in our past climate. And so we use global climate models, or GCMs, as tools and use them to kind of look forward, because the physics of our atmosphere doesn't change, just the amount of these greenhouse gases, such as carbon dioxide. So let's look at what a global climate model tells us about some of the changes in our Earth's climate. So first, we don't have data for the future. We don't have observations for the future. And so we can't force the climate models to that. So we have to think about some scenarios. So what might possible changes in our greenhouse gas concentration and other radiative forcings, dealing with land use change and other things, what might that look like out to the end of the century? And so we have a number of these scenarios that are used in the Intergovernmental Panel on Climate Change and the National Climate Assessment that are input into these global climate models. And there are three really commonly used scenarios called RCP 2.6, 4.5, and 8.5. We always have to use acronyms for everything. So RCP stands for Representative Concentration Pathway. So this is a time sequence or a pathway through time of how the concentration of greenhouse gases might change under different types of conditions. RCP 8.5 portrays kind of this unceasing increase in greenhouse gas emissions until the end of the century. And at the end of the century, it's adding essentially about 8.5 watts per meter square. You can think of an 8.5 watt light bulb in every square meter of our Earth on at all times. And so that's the additional energy that would go into our climate system by the end of the century. And we typically call this scenario the business as usual scenario. So it's the direction that we're currently headed in. RCP 4.5 represents kind of a stabilization and reduction of emissions around 2100 using a variety of strategies and technologies that we might see develop in society. And then RCP 2.6 is what's called the peak and decline scenario, where we really aggressively get after our greenhouse gas emissions, and they're reduced very significantly within the next decade or two. This is the rapid reduction that that Don and Jason were talking about that's needed to bring our system back into some semblance of what it's used to. So we plug these scenarios into the 20+ global climate models, and then they go away and compute for months on end. And then at the end, we analyze the output. And we're looking primarily for changes in the future. So we typically look at change maps. So for example, here, if you look at RCP 8.5 in the red line, we see that These global climate models, all of them, there's kind of a light swath of red that shows the difference between all the different global climate models. But in general, we see that these GCMs are projecting that by the end of the century, our globally averaged surface temperatures will be 3 to 5 degrees Celsius warmer than the recent past, about the past 30 years. For RCP 2.6 in the green, these globally average surface temperatures are projected to be 0 to 1.5 degrees Celsius warmer than in the past. So when Don was talking about the Paris Accord aims at a 2 degrees Celsius with a strong ambition for 1.5 degrees Celsius. So when you think of the Paris Accord, you might think about RCP 2.6, because clearly what scenario and the choices we make now make a huge difference. And you can see that difference in maps of these different variables that we can plot through the global climate model projections. So to read these maps, there's a number of things. First, you have to know what is the variable that we're projecting. So in this case, it's the change in the average surface temperature over time. You have to know what scenario you're looking at. So the peak and decline, or RCP 2.6, is on the left. RCP 8.5, or business as usual, is on the right. And then you also need to know the time frame. So this is doing projections for the late 21st century, or what we sometimes refer to as end of century. And you can see that in both cases, our temperatures increase globally, but RCP 8.5 is clearly much warmer than RCP 2.6. So these are kind of the big picture projections using the global climate models, but you want to know things on a more local basis. And so what we do is something called downscaling, which gets the output to be more meaningful to you on a local level. In downscaling, we take the global climate model output and we move it to what we call a higher resolution grid, or we have more of these grid boxes. And so it's like going to a high resolution TV. You can see things a lot better. And so for the downscaling that I'm going to show you here, we've used statistical relationships, looking at what the relationship in the historical period has been between the GCM output and local weather station observations. And we take those relationships and we apply them then in the future. And that's going to get us from a grid spacing of about 60 miles by 60 miles for a grid box to a downscaled grid spacing of about 6 miles by 6 miles. Now, we downscale the GCMs to answer your local questions. And this is especially true in areas of the world where we have mountain ranges and coastlines and urban areas and other things that have fairly strong differences across the landscape. For my center, the South Central Climate Adaptation Science Center, or CASC, I'll refer to it as. For the South Central CASC, we use what's called an ensemble approach to develop our climate projections. So in this approach, we use 3 scenarios. I'm just going to show you 2 in the slides forward, the RCP 2.6 and 8.5. We use 3 global climate models, 3 statistical downscaling techniques, and those are trained on 3 different historical observational data sets. And we're going to downscale these to these grid boxes, like I said, of 6 miles by 6 miles. And what we produce currently is 3 different core variables. So this is the daily maximum temperature, the daily minimum temperature, and the daily precipitation. And in the data that you'll see, will convert frozen precipitation into its liquid equivalent, where we have snow and ice. But from these 3 variables, we can actually create lots of other products, or what we call derived variables. So for example, since we know maximum temperature on a daily basis, we can calculate whether the number of 100-degree days or hard freeze days are changing. We can also look at specific types of events, like the maximum rainfall in a consecutive 5-day period. So what do these products show to us? And in particular, what are they showing in our region? So all of these maps are going to look somewhat similar. So I'm just going to walk you through the first one here, so that you know what you're seeing. So first off, because of this ensemble approach, what you're seeing is an average of the 27 projections for each scenario. So there's 27 projections going into the left map, 27 projections into the right map. The left map is what we call the low scenario. This is the RCP 2.6, the peak and decline. And then on the right is the high scenario, RCP 8.5, or our business as usual. And each of these maps that I'll show you will display the projected change. So this isn't going to be the low temperature, but the projected change in the low temperature over the region, and we compute that change based on whatever period we're looking at. In this case, we're going to look in the mid-century of the 21st century, and we're going to compare that to the recent past. So our recent past is from 1981 to 2005, so within your lifetime. And so here, our mid-century period is going to be from 2036 to 2065. So this map is going to show, or these 2 maps show you the projected change of the average low temperature. So Jason talked about low temperatures in the winter time, but this is by mid-century in the peak and decline on the left, and the business as usual on the right. And low temperatures can affect the health of humans and wildlife, because we know that our bodies tend to recover from heat stress during the night. In the low scenario, the average low temperatures across the region are projected to increase by about 1 to 3 degrees Fahrenheit by mid-century. And in the high scenario, we see that the average low temperatures are projected to increase by 4 to 6 degrees Fahrenheit. These changes are smaller near the Gulf Coast, and then they increase gradually as you move northward. So that's mid-century. The projections for the end of century indicate that the difference between the trajectory of these 2 scenarios is large. And so this is really important, because while we're making all of these changes, hopefully in the next 10 to 20 years, we might not see a great difference at this period of time in the mid-century between these 2 scenarios, especially for some of our variables that we look for. But what we're trying to avert is this end of century projections. So we see that if societies can respond quickly and significantly to climate change, then we can keep our average low temperatures to only about 1.5 to 2 degrees Fahrenheit warmer than today. But if we continue on our course as business as usual, then these low temperatures are projected on average to be about 6 to 10 degrees Fahrenheit warmer than our recent past. And in that case, and in all of these cases for business as usual, we would have to do much more adaptation for our communities and our households than if we can mitigate this climate change and aim at the RCP 2.6. Now, I want to mention that our level of confidence in the climate projections of temperature is very high. There's a direct relationship between more energy in the atmosphere and higher temperatures. Our 21 projections for all of the temperature-related maps that I'm going to show you are extremely consistent. So no matter what combination of GCM, downscaling technique, and observational data set that we use, we're seeing very similar results. These results also align with the National Climate Assessment, which uses different downscaling technique and more GCMs. So here is the projected change in the annual average high temperature. So warmer winter temperatures can lead to more insects, pests, and overwintering wildlife, but it can also decrease energy usage. Warmer summer temperatures can stress water supplies and increase energy usage. And similar to the low temperatures, high temperatures are projected to warm by mid-century, ranging from 1 to 6 degrees warmer than the recent past. Again, the Gulf Coast sees the least change, and parts of Kansas see the greatest change. We can slice this data by season. The top row shows the maps for mid-century and the bottom for end of century. And both of these are for the high scenario, so the RCP 8.5. And while temperature changes are similar year-round, we unfortunately, especially for me, I hate summer temperatures. We unfortunately see the greatest temperature increases during the summer. Now let's look at the change in the number of days when the high temperature is warmer than 100 degrees. So I really wish these days would just vanish. But even in the low scenario, we have a projection showing about 20 more of these days. So remember, these are change maps. So this is more than what we've seen in the past, recent past. So about 20 more days across Kansas, Oklahoma, and Texas, and southern New Mexico. For the high scenario, then portions of southern and southwest Texas are projected to have more than a month more 100-degree days than what we've seen in the recent past. And if there's ever a map to convince you to make changes now in the face of climate change, I think this is going to be it. In the high scenario, by the end of the century, we project 1 to 3 months more on average of days of 100 degrees. Let me say that again, 1 to 3 months more on average of days above 100 degrees. And recall that we're very confident in our climate projections. These high temperatures undoubtedly will stress both natural and agricultural systems, water supplies, wildlife, and us. Now let's look at precipitation. This product shows the projected change in the average yearly precipitation total. So values are in percent change from the recent past to the mid-century. Negative values mean that our total annual precipitation is projected to decline in the future. Annual precipitation may affect how much water is in our lakes, but people usually care more about the timing of precipitation. So this product may not be very helpful to you, certainly not as much as the annual temperature was. And what we see here is in parts of the Great Plains, we see they're projected to be about 10% drier in the high scenario and little change in the low scenario. However, this ensemble average, remember all of these maps are ensemble averages of 21 projections, doesn't tell the full story. And so this is what I mean. At the top is that ensemble average for the low scenario, RCP 2.6 that we just saw on the last slide. The projections used to create this ensemble average fill the rest of the screen. So we took these 27 projections, we averaged them to get that top map. They're grouped by the global climate model that they were downscaled from. And it's pretty clear that the GCM has a heavy hand in the precipitation projections. And not every GCM projects the same direction of precipitation change. So these temperature projections are pretty straightforward. They're like making scrambled eggs. Even I can do that. Precipitation projections are more like making a souffle. There's a lot more ingredients into getting precipitation to occur. Now, in some places like the Northeast and Southwest US, most of the models do agree on the direction of change. Unfortunately, we live in a part of the country where different GCMs are producing different results. Some are wetter and some are drier. And this is one of the reasons that we encourage folks to partner with us at the South Central CASC or other climate science partners, because we can help you interpret the products according to the type of decision that you need to make. So in some cases, the differences in projections won't matter for your location and your decision, but in other cases, they may be really important. So if we go back to the mid-century change map, we see the low scenario projects changes that range quite a bit from the ensemble average. However, that range was not as large in RCP 8.5. Most of the high scenario projections show that there will be less rain or snow in much of the western part of our region, though the models somewhat disagree on how much change that might be. There's a similar story for the end of the century. The GCMs have different areas of wetter, drier in the low scenario, but they're fairly consistent that there's a large region that will be drier in the high scenario. Now, our next map shows the projected change in the annual average number of days with at least 1 millimeter of precipitation. And so we call these rain days, even if there's snow involved. And with the annual precipitation product, all of the rain could have come in one single day. So this product gives us a better idea of how more or less often we might have a rain day. In RCP 2.6, the low scenario, there's not much change in the number of rain days by mid-century. But on RCP 8.5, we do see an average decrease of 2 to 5 days of measurable rain. Similar to the mid-century, the low scenario for the end of century shows little change in the number of rain days as compared to the recent past. And our confidence in the locations of those light yellow and light purple regions is pretty low for RCP 2.6. On the other hand, with the exception of Louisiana, the projections for the high scenario are consistent, and they indicate that there will be 5 to 15 fewer days on average of precipitation. Now, one of the GCMs shows a slight increase in rain days in Louisiana, and the other two show a slight decrease. So our confidence level for Louisiana is less. Now let's look at the number of days with precipitation greater than 2 inches in a single day. So these days can result in flooding in low-lying or poorly drained areas. And in contrast to the last product, these change maps have more consistent patterns in both scenarios and in both time frames. So our confidence level is moderately high for these projections. What you can see here is the western half of the region is projected to see little or no change in these heavy rainfall days. However, the east half of the region is projected to see one more day of 2-inch rainfall at least every other year by mid-century. By the end of the century, in the low scenario, the Texas Gulf Coast is projected to experience another day on average of these 2-inch rainfall events. In the high scenario, far eastern Oklahoma and into northern Arkansas are projected to see at least one more day on average each year of these heavy rainfall events. And these results are important for long-term water planning, such as the construction of stormwater management infrastructure. Our last product is the projected change in the maximum amount of rainfall that occurs over any 5-day period during a year. And these events usually are from slow-moving tropical storms near the Gulf Coast or multi-day thunderstorm complexes that travel from the high plains into eastern Oklahoma and western Arkansas, where they can stall. These events can bring extensive flooding across a broad region. And so here we look to see if these events will dump more or less rain in the future. For the mid-century, 2 regions are highlighted in both scenarios. Along the Gulf Coast, we project an increase of 1/2 inch to a full inch of more rain in these big 5-day rainfall events. And the projections going into this are mostly consistent. We have a moderately high confidence here. However, in eastern Oklahoma and western Arkansas, our 27 projections don't agree. In some cases, they show a decrease, in other cases, a large increase, so we have low confidence in this region. In the end of century projections, the Gulf Coast and southern Texas are projected to see more rain during these maximum 5-day rainfall events. Some places may even average over 1 inch or more of rain during these extreme events. There's also a large blob over Arkansas in the high scenario, and the models and downscaling techniques do not agree on this bullseye. So we have more products. I'll stop here. I'll remind people that climate projections are not forecasts or predictions like we see on our weather apps or TV broadcasts. Please work with climate scientists as you start using these projections to help interpret the information. And our CASC is here to help you. As you get familiar with the projections, the interpretation becomes much easier. Also remember that we have higher confidence in the temperature projections than in the precipitation projections. But even so, we know that the soils will dry and ecosystems will become more stressed as warmer temperatures lead to higher evapotranspiration, even if the amount of precipitation stays the same. You can find us on social media and the web, and I'm happy to answer your questions.
Thank you, Renee. I think you have a question in your chat box.
All right. Let me escape back here. All right. I have a few questions. So how many total grid boxes are planned to be used, and how will the grid boxes downscale to 6 by 6 miles or 5 kilometers or higher altitudes be measured? So I'm sorry I didn't see this when you probably had the question. So I'm gonna guess, Theodore, on what that where that question was. So I actually don't know the total number of grid boxes in our projections that we saw on the maps. There are a lot of them, and I can ask and find that out. The locations in New Mexico where we have much more elevation changes, 6 kilometers is still, in many cases, too coarse of a resolution to get really good climate projections there. We can see the general trends, but there are ways to do climate projections at a point. If you have enough data at that point for a long period of time. So this is one of the reasons why we really encourage those of you who have tribal lands to create kind of a long-term monitoring program, because once you have about 30 years of data, you can do direct statistical downscaling and climate projections at those locations. And so if there's some locations that are really important to you that you've been monitoring for a while, then you can get more detailed climate projections. Unfortunately, right now, we don't have the computing power to do higher resolution, but we're looking at that for this next step in the global climate models. So we're going from the global climate models using what was called, you might have heard the term CMIP5. I won't worry about the acronym, but we're moving to another phase called CMIP6 for the next set of assessments. And some of those models have higher resolutions, and so we can get some more detail in that. But for the statistical downscaling, we cannot get any more detail in the downscaling than we have the long-term weather station record from. And so there's going to be a limit on how much information that we can get at a really high resolution. Let's see. So let me look here. Okay. So during the pandemic shutdown, there was what appeared to be a rapid clearing of greenhouse gases, or even clearing and cleaning of some of the waterways. Has any of this observed data been incorporated into the climate modeling? So that's a great question. So we did have a year where people weren't driving around as much. We weren't flying planes as much. So we have seen some of a blip. Unfortunately, that blip we're coming out of the blip now. And many of these global climate models have to be run several years in advance of an assessment, just because it takes so long to do that, to check the data quality, to do to put all the products together, to put them on the servers so that people can access and use in the scientific community. That takes a number of years. So the current climate projections that are going into essentially the next set of assessment reports will not have that information in it. But once we get to what I assume will be called CMIP7, the next phase of that project, those data should be available for the climate models. So great question there. I see Don is helping answer some of the questions here. Thank you for that. Are you familiar with the UW's climate or tribal climate tool? Yes, I am, and I know that there's also work on translating that tool to other regions of the country, which we're pretty excited about. So for those of you who haven't seen it, our partner CASC in the Northwest is led out of the University of Washington. And so their team has developed an online tool that merges some of the projections and can get you fairly specific information for the tribes in that region. And that tool hopefully will be broadened across the US over time. Karen, do you see any other questions that I missed?
No, I think Donald just made another comment in the chat box, but I don't see any other questions just yet. Yeah, he just put in a link. No, let's see. I did get a request for the presentations, so I know I have yours, Renee, and Donald. I think you've sent me yours. So Jason, if you don't mind sharing, if you'll send that to me, I'll be sure and send that out to everyone. Theodore, please remind me if I don't remember to send you the PowerPoints, but I do have your email address. So I don't see any others in my chat box. Do you see any in yours, Renee, or Donald, or Jason?
I do not.
I don't either.
Donald, did you see any in your chat box?
No, he didn't, but I want to thank everybody, Renee and Jason, for the amazing presentations and all those people who participated. And Karen, thank you so much for hosting us today. Tribal people, we really got to get working on this, and I'm really excited that you guys are putting this at the forefront. Thank you so much.
Thank you, Donald. So I just wanted to let everyone know that if you have a question that we didn't get to or missed somehow, or you think of a question a little later, please just send it to me and I will be happy to forward it on to the presenters. So with that, thank you, Donald, Jason, and Renee. Thank you so much for presenting with us today. Great information. And everyone, don't forget to join us again this afternoon. Our next session is the Tribal Project session, and it starts at 1 o'clock Central Daylight Time. So please join us this afternoon for our next session, and everyone have a good lunch. And again, thank you for the presenters, and thank you so much for everyone attending. Have a good day. Thank you. Bye-bye.
Thank you.